Last time we talked about the conservation of momentum in the context of things moving just straight back and forth, like two things moving north-south, east-west, something like that. This time, we are going to add angles to it. Okay, so when two things combine, so when a car T-bones another car, like that, then momentum should still be conserved. It's just that it's a little bit more complicated. So we're going to do two examples that are two different difficulties. So we're actually going to start with the second example because it's a little bit more straightforward than the first example. If you remember when we first did tension, so a box hanging from two cables and the cables are angled, there were mild, medium, and spicy versions of that kind of question. The same thing is going to happen here. Okay, so let's get started. A 2,000 kilogram car traveling east at 24 meters per second enters an icy intersection and collides with a 3,600 kilogram truck traveling south at 10 meters per second. If they lock together during the collision, what is their velocity after impact? So I'm going to draw some pictures over here. Let's go like this. So before impact, we've got a car traveling this way, and we've got a truck traveling this way. Okay, they are going to collide with one another and lock together. So if then we go over here for the after side, after collision, they become one object. Okay, so we have our car and truck that have locked together into a car truck. Okay, now the conservation of momentum says that the momentum that was present before collision is also going to be present after collision. Okay, and so what that means for objects traveling in different directions like this is that there's X momentum present at the beginning and there's Y momentum present at the beginning, and the same amount of momentum in the X and Y direction will still be there at the end. It just may have been distributed differently somehow. That came out really weird. Okay, so what we're going to do is kind of catalog all of the information we have about the car and the truck before the collision, and then see what happens after the collision. So we know that the mass of the car, MC, is 2,000 kilograms. We know that the mass of the truck is 3,600 kilograms. We know that the velocity of the car at the beginning, VC1, is 24 meters per second. And it turns out that's an X component. Okay, the car is traveling perfectly horizontally. And so we're going to call this VC1X. Okay, now in this case, we didn't really need to say X because it doesn't have a Y component to its velocity. There's only an X component. And so this is just not always going to be relevant to the situation you're working on, but I'm going to put it there just because we are going to use it sometimes. So VC1X, so the velocity of the car at the beginning in the X direction, this is going to be really fun, is 24 meters per second. Okay, the velocity of the truck at the beginning in the X direction is nothing, right? The truck is traveling just vertically. Well, vertically. It's moving north-south, right? It's moving south. And so its X velocity is 0 meters per second. Okay? The velocity of the car at the beginning in the Y direction, VC1Y, is 0 meters per second. It's not traveling in the Y direction at all. And the velocity of the truck at the beginning in the Y direction is 10 meters per second. Okay, and that'll be south. All of this stuff, we can make it a little bit simpler when we just look at the beginning. What is the momentum that's present at the beginning? That's the same momentum that's going to be present at the end. So if we use P1 equals P2 in the x direction, this is going to be true. The momentum at the beginning in total in the x direction is going to be equal to the total x momentum at the end. Okay, so we can just look at what are all the x momentums that are happening at the beginning, and that's just the car, right? The truck doesn't have any x momentum, so all of the x momentum at the beginning comes from the car. So then we're just going to go MC V C 1. I'm not going to put the x on there because it doesn't have any y velocity, so this works just fine, equals M car truck, M car truck, V car truck at the end in the x direction. Okay, so what this is saying is that the momentum of the car at the beginning is in the x direction is going to be equal to the momentum of the two things locked together in the x direction at the end. Okay, so the x momentum at the beginning has been transferred to the end, and it's also going to be there at the end. We can say the same thing about the momentum in the y direction. P1y equals P2y. So all the y momentum at the beginning is equal to all the y momentum at the end. So the only thing with y momentum at the beginning was the truck. So we can just go the MT V T1 is equal to M car truck V car truck Y. No, 2y is what I wanted to say, right? Let me just fix that real quick. 2y. There we go. So the momentum of the truck at the beginning in the y direction is equal to the momentum of the car truck, the thing put together, in the y direction at the end. So let's calculate the momentum of the car and the momentum of the truck, and then basically we're just going to put those two things together. Okay, so when we do this, we end up with 2,000 kilograms times 24 meters per second. Okay, 2,000 times 24 is 48,000 kilogram meters per second, and that's to the east. Okay, so this is going to be the x momentum of the car truck in the end. Then we look at this part. If we figure out the momentum of the truck, we have the y momentum of the car truck. So that's 3,600 kilograms times 10 meters per second. Come on. Which is 3,000 or 36,000. 36,000 kilogram meters per second. To the south. Okay, so this is the x momentum at the beginning. This is the y momentum at the beginning. And at the end, since momentum is conserved, the car truck has to have the same momentum as it did at the beginning, as the separate parts did at the beginning. So we know that the momentum of the car truck at the end is going to be this 48,000 that way, plus this 36,000 this way. 48,000, 36,000. Okay, and so the total momentum of the car truck is going to be those things put together. So this is P of the car truck at the end. PCT2. All those subscripts, hey? So when we put those two things together, we get 60,000. Okay, so A squared plus B squared equals C squared. So we get 60,000 kilogram meters per second. So PCT2 is 60,000 kilogram meters per second. So that's the momentum of the car truck. We also should figure out the angle, because this is a vector and it has to have a direction. So we're going to do the inverse tan of 36,000 over 48,000. Okay, and when you do that, let's put this angle in here. And when you do that, you get 36.9 degrees. Okay, but this question's asking us what's the velocity after impact. It's not asking us for the momentum, but because we know the mass of the car and the mass of the truck, we can figure out their velocity just by taking the momentum and dividing it by the mass. So our last piece here, the velocity of the car truck at the end is equal to 60,000 kilogram meters per second divided by their total mass, which is 2,000 plus 3,600. I'm going to write that whole thing in here. 2,000 plus 3,600. And so when you do that division, when you divide it by 5,600, you get 10.7. Okay, so the velocity of the car truck at the end is equal to 10.7 meters per second. And then our direction will be east, 36.9 degrees south. And that's the total. So what we did was we found out what is all the x momentum at the beginning, what's all the y momentum at the beginning. That's got to be the same as the x and y momentum in the end. And so we just put them together and calculate what's the missing piece. So in this case, it was asking us for what's the total velocity in the end. So then we figured out the total momentum at the end using components, and then we divided it by mass to figure out what the total velocity was.